So yeah, I'm Freddy. I work in the Astro department, but I'm looking into how we can treat skin cancer. So hopefully my talk today will provide some context as to how we made that happen. So as to our background, we're looking at treating non-melanoma skin cancer specifically. We're looking at NMSC because out of all human malignancies that we see throughout the whole world, this is the most common one. So of all human malignancies, about 40% are skin cancers, and then of those, about 95% are NMSC. So this one type alone makes up about a third of all human malignancies. So in the UK, we see about 80,000 new cases each year, and that's an awfully high number. And to put that into perspective, that's about as many seconds as there are in each day. So that's as many people get skin cancer each year. And unfortunately, although it's unlikely to kill you if you get it, because so many people do get it, we still get about 2,500 people dying from it each year in the UK. And that's about as many stars as you'd be able to see in the night sky on a clear night. So an awfully high number. And what's more is...
I think your mic's muted.
It's muted.
Oh, there you go.
Is it muted?
No, there you go.
I'm just not holding it close enough. Okay. And what's more is that despite us being really aware of the dangers of skin cancer, the rates are still on the increase. And that's because we're spending more and more time abroad on holiday in climates where we haven't, our skin hasn't adapted to withstand the sun. So, okay, we can all agree that NMSC is bad, so then what can we do about it? So essentially the problem is that within our skin, we have a tumor and some sort of lesion on the surface which we need to remove. So the way that we do that predominantly is the way that you'd expect, where we literally excise the tumor by going in with a scalpel and just cutting around the edges of the tumor and just removing the chunk of flesh containing all the nasty cells. So that's the main method that we use, but we do have some other methods. So we might also do things like curettage and electrodesiccation. So a curette is like a scalpel, but instead of a blade, it's got like a little metal hoop on the end. So you scrape away the top surface with that, and then you use an electrode to go in and electrocute the rest of the tumorous cells to kill them that way. We can also use cryotherapy, where instead of directly harming the tumor, we can use liquid nitrogen to freeze it to death instead and kill the tumor cells that way. Or we can also use something like radiation therapy, where we try and target the tumor cells with radiation to kill them, whilst hopefully leaving the majority of the healthy tissue unharmed. And the reason that we use all these methods, of course, is because they're effective methods of dealing with skin cancer. Otherwise, we wouldn't use them. But that's not to say that they have considerable downsides associated with them. So they're all invasive methods, which means that they all lead to things like scarring afterwards. So as well as a patient having to deal with things like cosmetic damage as a result, it's also unsuitable for people who can't or don't want to undergo any sort of surgery. It's expensive. We're expected to spend about £180 million per year through the NHS treating just NMSC alone by 2020. And also the whole process for the patient can be quite tedious. If they first have to go and get diagnosed with skin cancer, and then they have to go back to get it treated and then also spend time recovering, the whole process can be quite an ordeal. So ideally, we'd like a method which managed to avoid all of these different things. And one such method is photodynamic therapy. So we'll come on to how it works in a second, but essentially why we want to look into it is because it's a non-invasive method, which means that there isn't any cosmetic damage. It's not a surgical method, it's a clinical method, which means that it is suitable for people who can't undergo surgery. And as it's a clinical nurse-led method, it's a lot cheaper than the surgical methods, and therefore a lot easier for the patients to go and get treated, because there's no recovery time associated afterwards. And the treatment only lasts about an hour or so. So how does the treatment work? Essentially, the first thing we do is locate where the tumor is, and that's quite easy to do. We can usually see it. We apply a cream to the surface of the skin, and that cream contains a prodrug, which is then absorbed into the skin and then metabolized into a photochemically reactive drug by the natural metabolism of the cells. But because the tumor cells have a higher metabolism than the surrounding healthy tissue, they build up this photochemically reactive drug at a higher rate than the surrounding healthy tissue. And we can activate the drug at any moment we choose by targeting it with visible light. So if we choose a time where the drug has built up a lot within the tumor, but not the surrounding healthy tissue, we can activate the drug, which causes it to release a free radical and kill the tissue, and it will only kill the tumor rather than the surrounding healthy tissue. and therefore there isn't any sort of cosmetic damage afterwards. We're only getting rid of the bad stuff. So it sounds good, so why don't we use it all the time? Well, the problem is that it relies on a combination of three things being there in order to work. We need enough drug to be able to be activated in the first place, and we can get enough drug throughout the tumour. And we need enough oxygen to be able to get there in order for us to release a free radical. And at the first instance, we also know there is enough oxygen. But what we can't get is enough light to penetrate deep enough in order to activate the drug at the depths of the tumour. Our skin is really, really good at scattering light away, and therefore we can't penetrate deeper than a couple of millimeters or so, and therefore the bottom half of the tumour can't be effectively treated. So, and we know that even if we can treat the top half of the tumour, if we don't treat the bottom half, it's just going to end up growing back and coming back. And therefore, this treatment at the moment isn't useful for people who have thicker tumours and thicker lesions. So obviously, we want to then ask, can we fix it? Can we find some way to deliver that light to deeper depths of the tumour in order to treat a wider range of patients? So the standard treatment method at the moment is just to shine the light directly above. But if we want to illuminate the tumour from the bottom, maybe we can try and do something like change the position of the light source. So maybe shining light from the side, or using a different wavelength, or flashing the light on and off, or any number of different things might improve our light delivery throughout the tumour. We don't know which of these things will work, but we know that some of them have merit, so we know where to start. So the question is then, how can we go about testing any of these things? Well, one route, of course, would be to do what medicine's done for the last 1,000 years or so, which is pretty much just empirically test it. We'll get some people who have non-melanoma skin cancer, and we'll try and treat them in different ways, and we'll see what works and what doesn't. And obviously, there's an ethical question with that. We can't try and treat people with a method which we aren't pretty damn sure is going to work. So for obvious reasons, clinical methods, clinical trials immediately are out of the question. So what instead if we make something that behaves and acts like a skin tumour, and we can try and treat that and work out what works best for that, and then apply it forward in a clinical method? Well, the problem is that first of all, it's very difficult to make a model that behaves exactly like a skin tumour. And then also, if we want to understand explicitly how our light is travelling throughout the tumour, we then still need to be able to measure it in some way. And doing that practically in a lab is extremely difficult. So again, for that reason, phantom testing is also not on the table. So, okay, so I'm a physicist, so maybe we can use theory to explain what's going on. Maybe we can come up with some equation that describes exactly how the intensity of light changes throughout the tumour. And it turns out that such an equation exists, and it's this one, if it will appear. There we go. Right? Not particularly pretty, right? And also, that only works if we make some really big assumptions about our person. So rather than the person being any sort of complicated human being, they instead have to be assumed to be some sort of spherical blob in space made up of just a selection of different layers, right? So for two reasons, this method is not applicable. One, people aren't made up of just layers, and also there's no way that I'm going to spend all day trying to solve this thing. So for one reason or another, analytical solutions are also out of the question. So that really leaves us with only one other method, which is, can we simulate what's going on? Can we pair a really accurate model of what we want to understand with some sort of code which will teach us how the photons would behave and interact with that model? Okay, and that type of code is what's known as a radius transfer code. So let's assume for a second that we can make a really good model of our skin. So what code can we use to teach us how the photons would interact with it? Well, this is precisely what astrophysicists have been doing for the last 5 decades or so. So all of our understanding of what's happening throughout the entire universe is taught to us only throughout this one picture we get of the night sky. And although it's a really beautiful picture and it's fascinating, it's somewhat silent, and we have to understand what's happening throughout the entire universe through only that picture. So for this reason, astrophysicists are the masters of understanding how light interacts with the universe. And they do this by developing these radius transfer codes, which essentially tell us how the light is interacting with all these different structures. So for example, we might have a wonderful picture of a nebula, And we might be wondering how much of this image is illuminated by one star placed here. So what an astrophysicist would do would be to take that image and they'd try and break it down and describe it in a simpler way, see what really matters. So they'd say, okay, we're interested in simulating this region of space. We know it's made predominantly of some sort of blue gas. There's some orange and some red pockets of gas here, and we can describe it simply just using these different structures. And then if we want to understand how much of the gas is illuminated from this one star, all we do is just put a star there, and we'd simulate what would happen if that star released one photon and how that photon would bounce around and behave with the gas and where it would travel. And eventually that photon might end up passing through the gas and eventually leaving the simulation. And okay, it didn't light up this galaxy, it didn't light up the nebula like we thought it might. So okay, we run another photon, and we see what that photon does instead. And this one, rather than bouncing around and leaving the simulation, we say it ends up bouncing right directly into our eyes, and that's how we see this part of the gas. And we do this again and again and again, and we do it for billions of photons until we end up with some sort of statistical map for what areas of the gas were lit up and illuminated for us by photons which originated from this one star. So then we can go back to this image and we can say, okay, if there was a really bright star here, we'd be able to see this part of the gas, and if there weren't any other stars, we wouldn't be able to see the rest of it. So okay, so that's clear how it might be used in an astrophysical context. So now I'm saying that we can take these codes and directly apply them to biology. And that might seem really strange, right? The physics might be completely different. But it turns out it isn't really. All we're doing is describing a different kind of domain, a different kind of system. It just happens to be a lot smaller. But the physics of what's happening is exactly the same. Light is still going to scatter around and bounce in the same way that it would do in outer space. It just does it a lot more frequently. So again, we describe our simulation and we say, okay, the majority of it's made up by just the normal generic skin cells. And we've got some regions of some sort of different tissue, maybe it's tumorous tissue here, and we'll describe it like that. And again, we'll say that we'll have another light source, but rather than it being a star, maybe it would just be an LED, for example. And we just run the same simulation. We just emit photons from our light source, we see where they scatter around, and we see what parts of the domain were lit up and what parts weren't. But in this context, rather than seeing what parts of a nebula we can see, maybe we're seeing what parts of the tumor are illuminated. And therefore, we know that any tumorous cells in this region would have been well treated because we could light them up quite well, whereas these parts weren't so well treated because they're a bit darker. So despite the situation that we're trying to simulate being very, very different, the physics is so similar and it's the same. So we can just take the same code and apply it in a slightly different way. The only thing we have to be slightly wary of is that the only difference between astrophysics and biology is that in astrophysics, things tend to be a bit fluffier. You can't land and touch most things. Like, you can't touch a star. It doesn't have a surface. Whereas when you're looking in biological systems, things tend to have nice, sharp, and solid boundaries. So things like reflection and refraction become a bit more important, which don't tend to be significant effects in outer space. So we have a code, and we know that we can use this code. So the only thing we have left to do is create a model. And again, we just describe it through a set of surfaces. So we pair each one of these surfaces with a different optical property. And then in combining the two, we then have a model which well describes what we want to understand, and then we have a code which can be used to probe that model. And we can describe all these things explicitly. So if we're trying to understand how best to treat a particular patient's tumor, we can make a model of that particular patient's tumor and then simulate that one to see what will work out best for that patient. So we take our model and we pair it together with our rate transfer code. And then we get a good understanding of where the light is able to travel and where it isn't. And we can try different things. So maybe we'll try some red photons and we'll see that they're the ones that manage to illuminate the top of the tumor. And then we can also run some yellow photons, and maybe those ones manage to probe a little deeper and manage to do a little better. And therefore, we'd know that we can improve the treatment for that patient by using a slightly different light source. So in conclusion, hopefully what we hope to do is use these codes to modify the general protocol to improve treatment for deeper tumors. And then going forward, because we can create a model that explicitly models individual patients, hopefully we can find some way to tailor treatments to individual patients and work out how to treat both a wider range of patients and those patients even better. So thank you very much. If you have any questions, I'm more than happy to answer them.